Hello, my lovely students. So now we are looking at section 6.3, which is on logarithmic properties. So we're going to look at the product rule, quotient rule, and power rule in this video. So we're going to look at them singly, then the expand and condense is going to put them all together and do lots of crazy stuff. So our first one here, the product rule, is if I am taking the log of a product, I can split that into the sum of individual logarithms. Now we use this rule in either direction. So the log of a product is log of m plus log of n. I get really tired of writing the little b's, so I don't. I just know if it's true for one type of log, it's true for all the logs. But the idea is to focus on the structure here, which is two things, and m and n can be all sorts of crazy things, but as long as the outermost operation there is multiplication, then it can be split to the sum of two individual logs. Likewise, if I have what I see on the right, two logs, same base, with a plus in between them, I can merge them into one log with a product. So our example here, log base 3, don't really care about the base, of 30x times 3x plus 4. I know gut reaction is get rid of parentheses. Don't do it here. Here, we're wanting to expand this into as many logs as possible. We need the outermost operation to be multiplication, not addition. I can't split a log across addition. So in here, there's the 30, there's the x, and there's the 3x plus 4. So that 3x plus 4 is going to be a thing that we can't break anymore. That's going to get its own log, but we can't break that log any more than that. All right, so my first one is 30. I could technically break that down more since it's a product of numbers, but usually we don't bother because this is a whatever it is, it's some number on a calculator. And here I'm writing the 3's because if you had to type this answer, you'd need the 3's. Like the log base 3's. So that is our answer. We could, and if you try to Google problems like this, those problems will often take the 30 and expand it more. Like I said, you can, you don't have to. But 30 is 6 times 5, which is 2 times 3 times 5. So this will become log base 3 of 2 plus log base 3 of 3, which we could actually turn into 1, plus log base 3 of 5, plus log base 3 of x, plus log base 3 of 3x plus 4. I'll put a little note here. We could write this just as like plus 1 plus all the rest. That's real tedious. I'm not writing it again. But that's why I said most of the time we're going to stop here, just splitting the product. The number part is something we can crunch on the calculator. And you're going to find in calculus, those kind of terms tend to be a, oh, yeah, it's the constant. It'll get sorted out later. And then you learn in differential equations, you spend the entire time finding the constants. All right, so here we have another one, log base generic b of 8k. So we can do this one a couple of ways, actually. So let's go ahead and dig in there. First and foremost, I see 8 times k. So I can just split 8 times k. I got my number parts separated. I got the k part. I could leave it like that. In fact, since we haven't, yeah, all right. But 8, I know, is 4 times 2, which is 2 times 2 times 2. So I could also write this as log base b of 2 plus log base b of 2 plus log base b of 2 plus log base b of k. And now log base b2, that's the same thing. I wrote it several times. How many times did I write it? 3 times. So I could rewrite it as 3 times log base b of 2 plus log base b of k. And I just gave you a preview of the power rule. But let's dig into quotients first. So when I have the log of a fraction, I can change that into a difference, whatever was on top minus whatever was on bottom, each with their own log. So what we're going to see in the example here, when there's multiple things, you got to pay attention to the pluses and minuses. All right, so log base 2 of 15 times x minus 1 divided by 3x plus 4 times 2 minus x. So there's a couple of ways to do this, but when you're first learning the rules, the outermost operation here is the division, the giant fraction. So we would handle that first by using our quotient rule. So we're going to split this into log base 2 of the top. And I'm putting some extra brackets just to be very careful about what is in there, what is not. And then minus log base 2 3x plus 4 times 2 minus x. All right, so I have technically applied the quotient rule. Woohoo! Now within these though, there is still a product rule. And on these kind of questions, what it's really just going to say is expand it as much as you can or compress it as much as you can. Since this problem started as one logarithm, then we would expand into as many as we can. So the 15 times x minus 1, that's a product. So I can break that into several logs. So log base 2 of 15, which could be broken into 3 times 5, but meh. Plus log base 2 of x plus log base 2 of x minus 1 minus, I'm going to put some big brackets around this next part because this minus is applying to this whole logarithm, but now we're about to split that into 2 logarithms with an addition in between them because it's a product right now. But this minus sign is going to end up being distributed through that sum we're about to write. So we have log base 2 of the first one, 3x plus 4, plus log base 2 of 2 minus x. So this minus sign is going to stick with this one, and it has to apply over here as well. So our next line, as long and tedious as this is, log base 2 of 15 plus log base 2 of x plus log base 2 of x minus 1 minus log base 2 of 3x plus 4 minus log base 2 of 2 minus x. There is our ridiculous answer. Doesn't that look simpler? That's why we don't say simplify, we say expand or compress. Which one you choose to do is based on the larger structure of the problem. We're not looking at those larger structures, so right now it is this is a thing you can do. Please practice it, so when you have a reason to do it, you're comfortable doing it. Which I find is like a horrible way to explain things, but that's where we're at. All right, so the x minus 1, no way to break that apart. That is log base 2 of x minus 1, period. Same thing with the 3x plus 4. I can technically factor out a 3, and then it'd be times x plus 4/3. We usually don't bother, though, because that gets ugly. The 2 minus x, I could consider writing that as negative x plus 2, or I could try to factor out the negative, but then you're going to run into taking the log of a negative, and we don't do that, so yeah, there's actually kind of caveats that go out with these when we get to 6.4 and start solving them. But for now, just assume whatever x's you're playing with would make the equation work. So this equation, there are not a lot of values that would work. In fact, I think it's just the numbers between 1 and 2. 1 because the x minus 1. I can't put a 1 in there, I'd get a 0, but anything a little bit bigger than 1 would work. And then the 2 minus x, if I put a 2 in there, I'd get 0. If I put in something bigger than 2, 3, I get negative numbers. So it's actually all the numbers smaller than 2. So it's just the numbers between 1 and 2, not including 1 and 2. There's our domain restrictions coming in. All right. Now we're going to expand this craziness. Now I do want you to know on the top, that is 7x squared plus 21x. That can be factored, and factoring will have an outer operation of multiplication, and we can split the log across that. And in fact, what we'll see is some cancellation. So on top, all I'm doing is rewriting the top. So 7x squared plus 21x has 7x in common. And that will leave me with x plus 3. And then my bottom has the 7x. And x minus 1. And x minus 2. So the 7 over 7, the x over x, like that's all being multiplied and divided, so we can cancel those. Meaning we do not have to write them in our final answer anymore. So now all we have to deal with is the x plus 3 over x minus 1 and x minus 2. Now I want you to kind of flip back, look at our previous one compared to the original structure. So I had the 15, the x, and the x minus 1 on top. 15 is positive. Log base 2 of x is positive. Log base 2 of x minus 1 is positive. Both of the things on the bottom ended up with a negative. So a lot of people will actually go from the start of the problem straight to that line. And that is fine. As long as it's making sense in your head, go for it. Just don't split the log too much. All right, so this one down here, I have log base 3 of x plus 3. That's on top, so I don't need to put a minus in front, it's positive. Then I have log base 3 of x minus 1. And I have log base 3 of x minus 2. X minus 1 is on the bottom, so it gets a minus in front of the log. X minus 2 is also on the bottom of that original fraction. It also gets a minus in front of it. That's it. Now, I want you to kind of pause and look at this, because on the next video, we're going to do this backwards. This is all expanding using the rules. I don't know, I guess I think of this way as more straightforward. But then when we do compressions and putting them back into one log, we have to do all those steps backwards. It gets a little weird. Now, power rule. This is what logs were designed for. This is what they do. So whenever we have log base anything that's reasonable of m raised to a power, the log takes that power, pulls it down in front of it as a coefficient or as something being multiplied in front. So I call this the power down because it brings the power down. So when we have the natural log of x squared, that 2 is the power, just like we see here. So that 2 is going to come down. So this is the same as 2 times the natural log, that's an L, ln of x. You can put parentheses around the x or not. But now here it's kind of like, yeah, sure, that's what it does. But what if we have an exponential where the x is the power? Oh, now this log just brings that power down. And now my x is on the line times some log thing, which is ugly, but the log thing is a number then. So therein lies the lovely power. So expanding a logarithm with powers, log base 2 of x to the 5th. Power comes down. Log base 2 of x. That's why I like the power rule. This one's a little more interesting. 2 ways to think about it. So one way is we always see is that x squared, but it's on the bottom. So I could write this using the quotient rule. So let me go ahead and do that. We would have the natural log of 1 minus the natural log of x squared. And then my power down rule is going to bring that 2. And so this is considered a -1. And then the 2 comes down as a product, so it'd be -1 times 2, would make this -2 natural log of x. Now what about the natural log of 1? E is a base, raised to some power equals 1. What power gives us a 1, regardless of the base? That is our good friend 0. So our actual answer is -2 times the natural log of x. I also, though, could have taken this original problem and written it with a negative exponent. The 1 over x squared, if I take that and move it to the top, remember that's our floor change. I take him out of his basement and say, you got to live here now. He is very mad at me. He liked his basement. He wants to go back. So he's negative. But now our power rule applies. -2 is the power. The -2 comes down up front, and we arrive at the same place. So there's no like one single way to expand logarithms, as long as you are careful about making sure you distribute when you need to, you pay attention to where your negatives are supposed to go, you'll be fine. Now this one here, a little more interesting. Log base 3 of 25. So, like, the directions here are rather silly. Expand using the power rule for logs, but there's no power. All right, but 25, I can rewrite. So log base 3 of 5 squared. Now we can bring the power down. And this is the kind of thing you would do when you had to calculate logs by hand. So you would have to go look up the ugly decimals for logs of particular numbers. And the more you could break the number parts down, there were only so many numbers that they actually bothered to calculate the logs of. So you wouldn't find log of anything for 25, but you would find log base 3 of 5. So you would have to know, well, 25 is 5 squared, the 2 comes down, so I just need to look up log base 3 of 5 and multiply it by 2. This is why modern day calculators are so amazing. And now a little preview of compressions. So 4 natural log of x, and it wants you to rewrite this as a single logarithm with a coefficient of 1. All right, so I don't want the 4 there anymore. The only equivalent expression is using the power rule, so I'm powering back up. So this is equal to the natural log of x to the 4th. And that's it. All right, we'll take a closer look at expanding and then compressing in the next video.